There is only one perfect solution, but there are clues that will try to trick our team.
Hello there, everyone. I'm Crazy Caleb, and today we are taking a look at a rather simple module, calculus. So what we need to do is, we need to, base off of this equation, we need to figure out whether we are deriving or we are going to be solving for integrals. And what this is basically changing the power of our solution. So first off, let's only worry about this equation up here. So what we're looking for is we need to solve this variable r of x in order to get one whole value. So what is r in this case? If the equation has variables f or r, replace them with the number of labels. And they word this a little weirdly. Labels is referring to indicators. So how many indicators do we have on the bottom? We have one. We have just one. So it's a 1 to the power of 3 plus another 1 to the power of 3. That becomes 2x to the power of 3. So now what we need to do is essentially derive to the power of 2. And how do we do that? Let's take a look down here. For those of you who are familiar with partial derivatives, this will be very easy for you. You can probably get done with watching this tutorial already. So we have our equation, a of x equals b, and we can follow along with this example here. So we have 5x to the power of 3, and then we have to multiply the constant by the degree, in this case being, what we'll do is, it'll be a times b, in this case. So 5 times 3 gives us 15 right here, and then we'll decrease the degree by 1. And that's how this module works. That's pretty much it for derivatives. So what we'll do is, since we're deriving it, we're going to simply multiply 3 times 2, and that'll give us 6x squared. And that's how we derive. And we submit the 6 here, and just like that is a solved module. That's all you do. All you have to do is just wrap your head around how to calculate derivatives, integrals, and it's just changing the power of the base. This is another derivative because we're going down in base power. So here we're taking a look at both m of x cubed minus 2 of x cubed plus r of x cubed. So there can be multiple hidden variables in here. So our mic is going to be a replace them with the number of port panels or port plates, as they refer to, and it says not the number of ports. And it says additionally here, if the two variables sum is greater than 9, divide both variables by 2. If it is not a perfect divide, round down. So we're looking for mic. We're looking for the number of port plates. In this case, we have 1, 2, 3, and that's it. So we have 3x to the power of 3 minus 2x to the power of 3 plus, what's r of x? R is the number of indicators in this case. So we have 1, 2, and that's it. So we have plus 2x to the power of 3. Now let's add it all up. 3 minus 2 is a 1, plus 2 is a 3. So we are given 3x to the power of 3. And that's what we're working with. Now let's get that derived to the power of 2. Let's go down here and do like we did before. Multiply a times b together and then drop the degree. So in this case, it's going to be 3 times 3, giving us a 9x squared. Just like that, we'll go up 9, and a solved module. Let's take a look at 2 more examples. Hopefully we can get an integral in here. No, we cannot. Okay. Let's take a look at another example, and I'm going to be probably doing this most in my head. So this is a 0, this is irrelevant, so all we have to worry about is f of x to the power of 3 and k of x. So f is the number of labels, 2 in this case, so 2 plus the number of port panels, 2 plus 1 is a 3. So we have 3x to the power of 3. Let's derive that. 3 times 3 is simply 9x, 9x cubed, and squared, excuse me. Same answer as last time. Hope we can get an integral here. Nope, we get a derivative. So we have here b of x to the power of 1 plus 0 of x to the power of 1. Let's take a look. So this 0 x is irrelevant. And a bravo to the x is going to be a, we're going to replace them with the number of batteries in the bomb. So we have 1 battery. So essentially, we're going to do this, a derivative, so that's 1 times 1 is 1. Now let's solve module. Now let's see if I can pop up and find an integral. But basically what an integral is this is how you're going to increase the degree. So we have the a times b here, and what happens is we add the degree by 1, and then when we add the degree by 1, we divide a. So what it's going to become here, as you can see here, we start off with 6x to the power of 2, then it goes to the power of 3, and then we divide 6 by 3, giving us that answer right there. Let's see if I can't pop up another one. Now, if you were to ever happen to get a weird division, you would simply round down, as it says up here. If it's not a perfect divide, round down, for example. Although I haven't seen a case where it isn't a perfect divide, but then again, I don't do this module that much. Let's take a look. Let's see if we can't get an integral. Oh my god, okay. R of x is the number of labels. Indicators in this case. So 2 minus 1 is a 1. So 2 times 1 is 2. That easy. Oh, good lord. Okay. R of x is indicators. Oh boy, we have indicators. 1, 2, 3, 4, 5. So it's going to be 5 minus 3 is 2. 2 times 2 is a 4. Cool. Oh, come on. E of x is the number of batteries in the bomb. 1, 2, 3, 4, 5. 5. Come on. Give me one, please. Here we go. Alright, so now we're going to be working with integrals in this case. And I'm so sorry it took so long and we got derivatives. I've never seen that happen so many times. So what we need to do is do like we always do and gather everything up into one variable. So m of x, once the lights turn back on, we're going to look for our port panels or port plates. 0 in this case, so it is irrelevant. Bravo X-ray is the number of batteries. We have 1, 2, 3, 4, 5. So a 5 plus 3. So we are working with 8x to the power of 1. So now we're going to essentially make integrate this into the power of 2. So we're going to add 1 degree to the power of 1, creating 2. And we're going to divide 8 by 2, creating 4x power of 2. Go up 4, and that's a solid module. As always, thank you guys for watching. I'm sorry it took so long for me to get an integrals example, but as always, stay crazy, stay cool, don't explode, and I'll see you guys later. Bye-bye.